Okay, so chapter 22 is about regression diagnostics. In the previous chapter, chapter 21, you learned about the simple regression model, how to find it, and how to find confidence intervals for B0, B1, intercept, and slope. And you also learned how to get the confidence interval for your prediction formula, right? So the problems we did on the previous chapter didn't have much problem regarding its variation. So you can see the problem we solve here, it doesn't have similar variances or doesn't have similar variation. It has changing variation. And we don't like changing variation for a regression model, and that's because it reduces the accuracy of regression, the reliability of regression model will be decreased, okay? So we want to make sure that the regression model that we are using to make decision is a reliable model, and it accurately, pretty much accurately give us some solutions. So in this example, we have price or cost of buying a home. That's your response variable. And you have size of homes. That's your X or explanatory variable, or IV, independent variable, right? So we can see that by increasing the square foot of the home, the price is increasing. But for smaller homes, what's happening here is the variation, the difference between home prices that have low square foot is not that much. They're very close to each other. The more we move to the right-hand side, you can see that the range or the variation in price is increasing. So start with a small variation on the right-hand side. By increasing square footage, you can see that is expanding and increasing, the variation become high. And why is that happening? That's happening because for larger homes, let's say you have a 5,000 square foot home, right? If each square foot price changes by just $10, the home price will change how much? $50,000. Every $10 change in a square foot will result in $50,000 change in home price, right? But you can see that for smaller homes, $10 change in the price, let's say it's a 500 square foot home, or 700 square foot home. Multiplied by 10, that's 7,000. That's not that much, right? That's what you are seeing here. So high variation for bigger homes, low variation for a smaller home. That is a problem. So we can figure out this problem on our data by creating a regression line. Of course, we have R squared. 65% of the variation in price is explained by the variation in square footage. Standard error is 91. Looking at your intercept, you can see that intercept is 50, and you can see a standard error is very large, right? That is telling us something's wrong with this model. Sample size is 94. Of course, larger sample size can also help us to get a better shape of our scatter plot. Also, we can look at a regression model. So that's a price, home price equals to 50.599 plus 0.159 times size of the home, right? But is this a significant model? The answer is no. Why? Because look at the intercepts p-value. For 95% confidence level problem, the p-value is supposed to be below 0.05. Is that number below 0.05? The answer is no. So this model is not really reliable for us, okay? However, for size, you can see that we have that reliability. This p-value is less than 0.05. So going back up in the scatter plot, you can see where the problem is coming from. It's coming from the changing variation, and that's resulting in a pattern. So you remember that we said residuals in the previous chapters, we said residuals are supposed to be normal. Residuals are supposed to have similar variances and independent. And independent means the residuals should not have any patterns, right? Pattern means changing by, when you change the explanatory variable, then you don't want to see any change in residuals, right? So you can see that residuals are increasing. Residual is the difference from the line, right? Difference of each point from the line is residual. So residuals are increasing as much as long as whenever we increase the square footage, right? So that is a pattern in residuals. So residuals are not independent. So this is what we already explained, and we explained this as well. Let's go to detecting differences in variation. So based on the scatter plot, the association between the home price and size appears linear. We have a linear relation. A little concern about lurking variables, and that's because of the variation change that we have. Since this sample of homes is from the same neighborhood, similar variances condition is not satisfied. And we just explained that. A good tool or a good plot to recognize if our residuals are having similar variances or not is the residual plot, right? The residual plot is the residual is on y-axis, and your explanatory variable IV is on the x-axis, right? So let's just, let me show you here on job data. Let me see if I have the 22 here. Job. Okay, so this is the home prices data. You can have access to this data from Canvas files, and then go to PPT files and find the folder 01 jump files, and open this file and download it. So price versus a square foot. Make sure you put minimal report here under emphasis and click run. This is pretty much the same as what you saw in the book, right? Let me show you. So you have low variation on the left and you have high variation on the right-hand side when we have increase in square footage. So another thing we want to see here, the R square, 67% is good. More than 50% is actually good for regression model. But that's not, the R square is not the most important thing. The most important in simple regression model is p-value. Is the p-value of intercept below 0.05? No. So this model clearly have some issues, right? And we can see that the issue is coming from the fact that we have this changing variation, and probably we have a lurking variable as well. That could be because the data is taken from the same neighborhood.
Professor, can you explain it again? How can we know if the p-value is good or bad? You compared it to 0.5, I think.
Where? Which one?
You mentioned when the p-value is good or bad. How can we tell?
Yeah, I can't say, I didn't say good or bad. There is a method, right? If we are using 95% confidence level for decision making, we're going to make sure that p-value is less than 0.05, less than 5%. So it's here. Do you see intercept and square foot?
Yeah.
That's your p-value under prop. Do you see when I put my cursor here, here it says p-value 0.18 is not significant. So it's not significant means that this intercept is not going to work for at least 95% of cases in the population. It does not represent at least 95% of the population. It's less than that. How much less? P-value is 18. That's probably somewhere around 80, 82%, 81%. Okay, so now it's time to check residuals, right? To check residuals, you click on the red triangle. There are several different ways you can get information on JMP. When I show you in a certain way, that does not mean that's the only method to get numbers. You may get these numbers in many different ways. So one way to save residuals is go to save column and click on residuals. That saves the residuals for you. You can see at the end of your data set, you have residuals set. Now, positive numbers are the points on the top of the line. Negative numbers are the points below the line, right? What else can I get? Now I have residuals. One of the graphs I can create is a scatter plot of residuals, right? So I go to fit y by x, take residuals as y response, and take my explanatory variable as a square foot, take it as x, and click OK. This is the residual plot, and I need to fit the line. Residuals plot has always a fit line horizontally. And that helps us actually to have a good judgment about the shape of residuals. Are these residuals represented symmetrically, almost randomly spread around the line, both up and below the line? The answer is no, right? Whenever you see triangles, that means we don't have similar variances. In this case, you can see, you see a triangle here, right? That means we have changing variation. What or how would that look like if it's not changing variation? You would see a rectangle or a circle symmetrically on top and bottom of the line. Question?
Yeah, Professor, when you say rectangle.
So that's one way to get the residual plot we want. And this actually is available on the slide. Let me show you. Look, this is the same plot, right? The residual plot. And here it's saying it's a fan shape. And that fan shape of residual plot indicates changing variation rather than similar variation. You can also create a box plot to see the variation. So something important in chapter 22, I just wanted to make sure we touch it, is when you do have similar variances, which is good for regression model, we call it homoscedastic residuals. Homoscedastic residuals is when you have equal amount of variation in residuals. If this assumption has not met, that means we have changing variation. We call residuals heteroscedastic errors or heteroscedastic residuals. Okay, so in this case, we have heteroscedastic residuals. And these two words are important because some homework and some exam questions they will use this word, and they will ask you which of the following is correct about these residuals. Then you may not remember the name homoscedastic, heteroscedastic. Make sure that you remember where you learned it and what it means. So continuing the changing variation, so what are the consequences of different variation? Prediction intervals are too narrow or too wide. Confidence intervals for a slope and intercept are not reliable, they're not accurate. Hypothesis tests regarding beta 0 and beta 1 are not reliable. And beta 1 and beta 0, we saw them in the table up here. right? So you can see that these two are not reliable. The p-value, especially the intercept, is not less than 0.05. So we can't rely on that value of intercept. So the model is not reliable in general. So you can see that the confidence interval, because of those large differences here, is expanded. This has increased. However, it is not representing those same for the small homes, right? What is the solution for us here? The solution is, so this is our formula. Price equals to the fixed cost multiplied by the slope of a square foot. So if we divide both sides of the equation by a square foot, instead, we are actually excluding the size of the home. We're just looking at price for each square foot, right? In this way, no matter what the size of the home is, the actual value of the home is being evaluated based on the square footage. So whether it's in a good area, expensive area, or a poor area. So we're excluding that from our calculations. So that's the calculation, simple calculation. We divide both sides by a square foot. So the new model will be price per square foot, not only price. And then you have the slope and F multiplied by 1 over a square foot plus epsilon. And epsilon is your errors, right? So fixing the problem, revise the model. The response variable becomes price per square foot, and the explanatory variable becomes reciprocal of the number of a square foot. So next is the marginal cost M is the intercept now, and the slope is F, the fixed cost. The residuals have similar variances with this new model. So if we graph the scatter plot one more time, but using this formula that we have now, you can see we don't have that triangle shape or fan shape. We have pretty much close variations. And the box plot also can confirm that. Next, we can check normality of residuals. How do we check normality of residuals? We check normality of residuals. Let's just see it here. We can use row diagnostics. And let's see if we have normal quantile. Plot residuals by normal quantiles. Click. Down here, you have the normal quantile. Next. So this is the new model. The new model doesn't have the similar variances problem. It has similar variances as a result. So let's look at the results. The most important things we look at is the p-value of the model, of the regression model. Are p-values below 0.05 in our decision? The answer is yes. Okay, so that's telling us that this model has become a reliable model now. Another sign that we don't have variation problem is SE, standard error. You remember it was 90 something. Now it's 39. It has reduced a lot. Considering that intercept is a large number as 157. And so now we can have our regression model. Estimated dollar per square foot equals to 157 plus 53,887 per square foot. We can also get the 95% confidence interval for the intercept and also for the slope. And we can actually get that here under parameter estimates, right click, go to columns, get the lower and get the upper 95%. Of course, we don't use this data. This is the one with the variation problem. So if we want to use the other one, I leave that for your practice. you use price as, so no, you use price per square footage. This one will be your response variable, and 1 over a square foot will be your IV. Okay. Now, you know where to get the confidence intervals and jump. This is confidence interval for intercept and slope. There is another confidence interval you need to get for the predictive formula, right?
Yeah, we're trying to find out what they are for a specific.
Next is outliers. So you know that outliers have negative effect on results. There are different ways to get outliers on jump. So let me show you really quick. So one way, this is one way you can find outliers on jump. Go to analyze, go to multivariate methods. Go to analyze, multivariate methods, and click on multivariate. So analyze, multivariate, click, and drag and drop your, so the initial model which had the problem has a lot of outliers. Let's check that. We take both price and a square foot as they both go to Y columns as our variables. Click OK. You have your scatter plot matrix here, but that's not what we are interested in. We want to find outliers, right? So there are different methods. This is one method that you can use. So down here, do you see it says outlier analysis? When you have your multivariate results, click on the red triangle of multivariate, outlier analysis, and Mahalanobis distance or Mahal distance, and jackknife. They're both quite similar. They just use different formulas and different methods to find a certain line that after that line, any point above that line will be outlier. So let's do Mahal test. And let's expand it. You see that? That upper control limit, UCL, is calculated based on Mahalanobis distance formula, which is sensitive to sample size, and that's very good for us, because if you have a smaller sample, it will adjust itself. And it's also sensitive to number of explanatory variables, so that's a good thing. So that line represents the highest, farthest point to be that is not negatively affecting results. Any point above that can be an outlier. So how do we know which point, which row is that? Just bring your cursor here. It shows which case it is, and you can right click, and first you have to select it, click on the point, and it's selected, it's not highlighted, right? Right click, and you can say row exclude or row hide, and that's how you can continue your deciding to remove it or not, okay? So that's Mahal test, and you can also do the other test. Jackknife also normally give the same answers, same points. Do you see that same points are selected? So they both accurately give you some outliers, okay? So let me really quick also show you. So this was outliers. And then there was a last part, which is, so you can check the outliers. So you can remove outliers, rerun the test, and see if the slope and R-square is changing. Some homeworks are actually just like that. They will ask you to remove this point and rerun the test. Does the model change? Does the R-square change? and you will say yes or no. And about detecting dependency, are our residuals independent? Durbin-Watson test is a good test to run. I really quick show you where to get it, but I will explain it next time together with the next topic as well. But really quick show you where to get the Durbin-Watson test. You go to, not this one. It's under model fit. So it's under this. This is our original results. So you go to red triangle, row diagnostics. Chapter 22 is diagnostics, right? And this is also row diagnostics. And you find the Durbin-Watson test. You see they match this one, Durbin-Watson, Durbin-Watson. You click. At the end of your results, you have Durbin-Watson test. And what are we looking for? The Durbin-Watson value has to be close to 2. First of all, if you want an accurate value, how close to 2? Depend on sample size is different. So the best is to check p-value. Where do I get p-value? In JMP, anytime you want to add information, red triangle. So go to red triangle and p-value. If the p-value is more than 0.05, if the p-value is more than 0.05, we have independent residuals. If p-value is less than 0.05, we have dependent residuals. I hope that makes sense.
Professor, how did you pull up that Durbin-Watson?
Okay, so that would be an example of residuals with dependency. So the best way to recognize this is just to look at your p-value, okay? The p-value of your Durbin-Watson test. And I think there has to be a hypothesis here. Yeah, the hypothesis null for Durbin-Watson test is the row, the relation, the autocorrelation between these residuals is 0. So if you reject it, they are dependent. If you don't reject it, they can be considered as independent. All right. I will explain this topic, the Durbin-Watson and autocorrelation next time when I teach you the next topic. So I just wanted to give you a heads up of what's coming next. And that would be for today.